Yeah, thanks very much. You're too kind. So a very warm welcome, everyone. Quite literally to our session on living in a quantum state. And like many others, you may be wondering, what exactly is quantum computing? After all, quantum computing seems to be everywhere these days. The interest, it seems fair to say, is going through the roof these days, mostly for good reasons, I'm tempted to say. But what is it? So in the first part of the hour, the trained physicist Jasmine Meiniker will explain to us the basics of quantum mechanics and also of quantum computing. Then in the second part of this hour, Libby Heaney, also trained physicist but also artist, will highlight the ways in which quantum computing is being embraced by the artistic communities, like explaining to us how the arts may help in understanding this relatively complex topic, but also how, say, subtle ethical considerations may or may not come into play. I should say that this session is co-hosted and co-organized by the Munich Quantum Valley. That's a major hub in research and development in southern Germany, and also by the Goethe Institute London, who's kind of setting up a series of events that bring together the arts and quantum physics through several events happening in London, in Dublin, in Beijing, in Berlin, for that matter, and also other places, kind of seeing to what extent this new technology can be approached through the arts. So now, living in a quantum state. So in some way, this is again happening in a way too literally, in the sense that, unfortunately, both Jasmine and Libby will only, well, they will be living literally in the quantum state and will be with us electronically. COVID has hit quite badly, so I feel a bit abandoned here all alone on stage, but I'm sure this will not take any energy away from this event. I can already see our first speaker. That's great. So let's get going. It's my great pleasure to introduce Jasmine Meiniker. You can see her here on screen. She's a trained physicist based in Munich at the Ludwig Maximilians University in Munich, but also at the Max Planck Institute for Quantum Optics in Garching. She's interested in the foundations and fundamentals of quantum physics, ultimately thinking about superposition and entanglement, and she will explain what that is in her little mini lecture coming up in a second. I should say, like, while I'm a dry swimmer, I'm a theoretical physicist. She's an actual experimental physicist doing experiments in the lab, and she's been doing exciting work with light, with quantum light particles, if you want, like putting a light quanta on chips and manipulating the quantum state of light in integrated optical devices. She studied physics in Göttingen and Hamburg, then moving to Bristol in the UK. That's a major hub for optical quantum technologies, to then come back to Germany. It's great to have you back as a start fellow in Munich and the Munich Center for Quantum Science and Technology, working at the Max Planck Institute for Quantum Optics in experimental physics. So we are very much looking forward to your presentation. So the stage is all yours, so I hope, and shoot it away.
Okay. Yeah, thank you, Jens, for the kind introduction. It's really a pity that I cannot be in Berlin today, but I'm still very excited to be part of Republica. So it's really great to see so many people being interested in quantum mechanics and quantum computing in particular. And indeed, recently, the interest in quantum technologies is growing also in the media. And maybe you have read an article, newspaper article about a company or university trying to build a quantum computer, for example. And maybe this is why you're here today. Maybe you're asking now, what's this quantum stuff really about? How does it work? Or maybe you're even wondering, should I buy a quantum computer myself in the near future? So in the next 50 minutes, I will try to explain some of these questions. And to give you one answer up front already, I would say it's not very likely that you will buy a quantum laptop, for example, yourself in the near future or even ever in your life. And the reason is that quantum computers, they are not just smaller and faster versions of the computers we have today. They are really something different. So they are working on the principles of quantum mechanics. And this is why they have really different capabilities and also very different requirements than our computers we have today. So to understand more about quantum computing, we first need to look at the computers we have today. And the computers we have today, I'll call classical computers, because quantum scientists, they tend to call everything which is not quantum classical. So what's a computer? So in the very beginning, computers were just human beings, like the woman you see on the picture on the left. They were called computers because they were people who compute. And they did calculations for astronomy, for example, and during wartime, they had to calculate missile trajectories. And with a growing demand on computing power, electrical computing machines, electrical computers have been invented, such as you see on the right side in this picture. This is one of the first electrical computers in the year 1945. And then some of these women who were computers themselves before, they became the first programmers of computers. So they did this here really by changing the wires on this machine. But then, so this is still pretty cumbersome, but then computers became smaller and faster, we all know. And for example, now the thing I have here, the watch on my wrist, is much faster than any computer in the 80s. So we know computers always are becoming smaller and smaller and faster and faster. And it's true, if you make things smaller and smaller and smaller, you will end up at the size of single molecules or even atoms. And these are behaving indeed as quantum particles. But that's not really the reason why people want to build a quantum computer, just because things become smaller. There's a more fundamental reason for this. There's a more fundamental problem with computation itself. So let's look at computations. How do computers compute at all? Let's look at a very simple example. Let's calculate 2 times 13. So when you give this question to a computer, what the computer does, first it translates everything in zeros and ones. That's just how computers save and process their data. They use bits for this. And then the computer needs to run an algorithm. That's just a recipe how to do the calculation. If we do the calculation 2 times 13 in our head, we also kind of use an algorithm. So I learned in school, I first calculate 2 times 10, then I calculate 2 times 6, and then I add both together, and then I get 26 out. So that's the task of multiplication. That wasn't so difficult yet. So you can also do the reverse calculation. You can ask, which numbers do I have to multiply to get 26 out? So, and we know from the example before, it's 2 times 13. So that was easy as well. But how about a larger number? What numbers do I have to multiply to get 143 out? I don't know if anybody in the audience does know the answer. I mean, how would you do this? The only way I know how to do it is to just try all the different numbers till I find out the right ones which fit. And then I will end up at 11 times 13. So this already seemed to be a bit more difficult for us, but also for a computer, the task of factoring is much more difficult than multiplication. For the number 143, it's still not very difficult. So any computer will be able to do this. But for much larger numbers, computers just cannot solve this efficiently and fast. There's no algorithm who can factor numbers easily. But okay, now you might think, okay, there's no computers can factor, but why should I care? This sounds to be like a pretty boring task. But in fact, we are using this every day. every day we go in the internet and we visit a secured page, we are using this fact that factoring is hard for classical computers. When you type in your credit card number and you send it off to some receiver, your number will get encrypted, and it will be encrypted by using a large number. And only the person who can factor this number, who can factorize, who knows the factors, can decrypt your message. And the receiver, he knows the factors because he sent you the large number beforehand, so only he can decrypt your message. But anybody who could factor numbers fast could break this encryption. So if you have a computer who can factor fast, you can read most messages on the internet, because we don't have a classical algorithm for our today's computers who can solve this. But somebody found a quantum algorithm who can factor large numbers much faster. So there is a difference between what you can do on a quantum computer and what you can do on a classical computer, what kind of algorithms you can run there. And to understand a bit more about the difference between these two different types of algorithms, I have another example for you. And this example is called random walks. I chose this example not only because I did a PhD on this topic, but also because there's a quantum version and there's a classical version, and you can nicely see the difference between both and how they work. So random walks are used in classical computing, our today's computers, to develop algorithms where there's some randomness inside, or seemingly randomness. For example, stock market prices, they seem to be quite random. So random walks are used there. Random walks, classical random walks, are also called the drunk man's walk. Maybe you know from your experience, you can imagine why it's called random walk. If you're drunk, you really pretty randomly walk left or right. And so now we want to look at how a classical and a quantum random walk can perform in solving problems. And the problem now should be walking home from the pub. So you have here the pub, and you have here our friend who had a couple of beers, and then you have home, where he wants to go. And now what you think, how he will perform. So he will pretty much randomly walk left and right. And you can imagine that, no, he won't come very far. So as a physicist, I really like to draw plots. So what I plotted here is the probability where he will end up after some time. And you see in this curve that the high probability is where the pub is, exactly there. And also pretty close to the pub on the street, it's also very probable that he will end up. But he will not make it home. The curve is really low there. And he also won't go to a second pub. But what if the walker can use the rules of quantum mechanics? Then this curve looks very different. You see here that at the pub, the curve is very low, but at home, it's very high. So he will make it really home, very probable. And he will also make it to a second pub, very probable, which you see on this curve. And the weird thing with this quantum walker is, as I will explain in the next slide, he will make it even home and to the pub, kind of at the same time, which would be pretty amazing if you could do this. So this fact that the quantum walker can walk much further away from its initial position, this can be used in developing quantum algorithms. And in these quantum algorithms, there are two principles, quantum mechanical principles used, which are most important. It's superposition and interference. And in the following, I will explain these two principles. So let's first look at superposition. So here I just plotted the classical walker, and what he will do, he will walk either to the left side or to the right side. He has to decide. This is how we are used to with these things. And in a computer, in a classical computer, you would call left and right. This would be your zeros and ones. This is a bit, left or right, on or off, one bit of information. But how is it for the quantum walker? He will not walk left or right. He will walk in this superposition, which kind of is both left or right, if you want, or something in between. If you write it down a bit more mathematically, you would write 0 plus 1. That's this superposition. But you can also write 0 minus 1, or you could also write other things in between. This is not a bit of information, this is a qubit. So in a quantum computer, these qubits are used. And you can have different kind of superpositions, different states of this qubit. And with this is then now important for the second ingredient to do quantum computation, interference. So first look how the world we see as it's normal. The classical walker, he walks as in this pictures, left or right, and then he has again the possibility to go either left or right. And then we can nicely explain the curve I showed you before here with this high probability in the middle. So to go to the very left, he has just one possibility. He has to go left. To go to the very right, he has only just one possibility. He has to go right and a second time right. To go to the middle, there are two possibilities. So this is why this is more probable. This is really basic classical probability theory. But for the quantum walker, it looks very different. So this quantum walker will go in this superposition. And as I showed you before, you have different kinds of superposition. And you can have a superposition with a plus sign and a minus sign, for example. And whenever you bring something together, something positive and something negative, this can cancel each other. So this is why you can here explain this curve. So in the middle, you can cancel these quantum probabilities, which we call amplitudes here. And this you can use then to develop quantum algorithms, which have really then different properties than the classical algorithms. So to do this, you need the interference and you need the superposition. To have interference, you need superposition, and to have superposition, the thing you need to do is you need to leave your quantum particle undisturbed. Because always when you look where the quantum walker is, of course, you need to, if you ask if he is home or in the second pub, of course, he has to be somewhere. He is not, he's just in the superposition. He is kind of in both places. But if you really look where he is, he has to be at one specific point. And as soon as you look, the superposition is destroyed. For a quantum computer, this means that you're not allowed to look in between how the computation is going, kind of. So this is why quantum computers are harder to build than our classical computers, because you need to destroy kind of all interference, all effects from outside. You need to isolate your quantum system very well. But today already people did actually build quantum computers. Here I show you a picture where when you Google put in a search engine quantum computer, this is a typical picture you will find. But what you see here, actually, this is basically a huge fridge. So all you see is to cool down the small quantum chip, which is at the very bottom, and you need to cool this quantum chip down so that it can maintain this superposition. And so this is based on superconducting circuits, this type of quantum computers, but there are also many other platforms, for example, atoms or ions or photons. But they all have in common that the systems you can build today and the things you can buy for a lot of money are still very small. So they have small number of these qubits I mentioned before, maybe 50, maybe 100 qubits. So we still need to scale up the system size, of course, to do any useful things yet. But maybe you think now, okay, I've shown the pictures of the classical large computers many years ago, and then we all know that they became much faster very soon. And you might expect that this happens also here with a quantum computer. But since quantum computers have really these difficult requirements, it's quite a large technical challenge to do. But as an outlook, let's look if we are able to build this quantum computer what they can do. So as I mentioned before, they can solve some very hard problems. For example, they can factor these numbers efficiently, which, okay, would be kind of a problem for our internet security. But then on the other hand, you can also use quantum communication, where your security is not based on the hardness of some mathematical problem, but really on the laws of quantum mechanics. Another thing you can use quantum computers for very nicely is to simulate other quantum systems. And this is really relevant for developing new materials, for example, because these are often also quantum systems you can then understand better and develop whatever better superconductors for energy transfer, for example. But then I also want to mention that there is not only quantum computing, which is maybe the most prominent example, but in quantum communication, there are also other fields of quantum technology, which is quantum sensing, where you can measure more precisely by using quantum systems. And there's also quantum information theory. So the task of, for example, of finding new other quantum algorithms, which can be better than classical algorithms. And then the area of quantum foundations, which thinks more about what the nature of quantum mechanics, what it means for the nature of our world. Yes, and to conclude, so we still have to put, I would say, some effort in developing quantum technologies, but it's really worth it because we can have really different applications and possibilities than we have now.
Yeah, thanks so very much, Jasmine, for this wonderful and enlightening talk. You have the chance to ask, well, you should and must ask questions to Jasmine later. But we first come to the second presentation, and then we have like the question round at the very end, where we ask each other questions. So let's change gear and do not change gear. When we turn to the second presentation by Libby Heaney. She's a British artist and also trained quantum physicist. In fact, I know her from her former life, being a quantum physicist, getting a PhD in Leeds in quantum physics, but then also getting an MA in arts from the University of London, where she's now a successful artist with exhibitions in the UK, but also in Montreal, Berlin, Melbourne, like all over the world, basically, presenting her work. So she's working with quantum computing, but also with artificial intelligence, and kind of puts together these tools in a way to see how and who they basically empower, and also who they basically disempower. She kind of puts things into interesting contexts and kind of sees how these technologies can be subverted to work against themselves, to kind of stress potential capabilities and potentials, but also potential risks and dangers that might come along with these technologies. That might sound a bit heavy, but I think it isn't. I mean, she's also known for bringing in surrealism, Dadaism, and humor. Her work's often kind of fun and also strange in a good way, putting us into a new contact with things and adding a kind of new level of perception to things. So again, she's with us electronically. If I can handle this very classical computer, I will present this to you.
Hi, I'm Libby, a visual artist based here in London. I also have a background in quantum information science, so a PhD and 5 years of postdoc experience. And this is relevant because today we'll be talking about we're talking about quantum computing, but also how arts in general can help audiences or help lay people, or just develop a collective understanding around this very new, often quite mysticized technology. So I'll start by showing you a video actually of an exhibition that was presented recently in Berlin with Light Art Space. This is a behind the scenes video, and I think it's a really nice introduction to what I've been doing. and then I'll come back and join you and we'll unpack some of the themes and so on. And there's a work that I'm showing with the Goethe Institute here at the Publica Festival, so I'll speak a little bit more about some of the visual elements and the themes in this work. So enjoy the behind the scenes video and I'll see you back in a couple of minutes. Thanks.
Quantum computing will change our world. For LRS as an art institution about the future, it was a necessity to address this with an art project. We are extremely proud that with End by Libihini, we enter the quantum era in the art world.
Quantum computing dissolves the binary. This means that inside a quantum computer, you have these parallel worlds where all possible futures all take place at once in order to get this really fast speed up compared to any digital computer. My name is Libihini. I'm an artist with a background in quantum physics and quantum computing, and now I combine the two in my creative practice using digital media to explore what quantum computing means for us now and also in the future. Quantum computing is a new technology that's still in its infancy. It's being developed by big tech companies and startups and universities around the world. Quantum computers rely on different laws of physics, quantum laws. Concepts like entanglement are key for quantum computers. And essentially what happens is, rather than bits, you have these quantum bits that can exist in 0 and 1 at the same time. So you can have many computations running at once inside the quantum computer. I take Bosch, Garden of Earthly Delights, as a starting point for this installation to imagine the possible futures of quantum computing situated somewhere between heaven and hell. So we start by falling from a quantum computer in the heavens, this all-seeing machine that's taken the place of kind of this all-seeing kind of God or religion now. And when we fall through the sky and encounter these quantum creatures, which are actually based on my scans of my watercolour paintings. And these have been animated using data from quantum computers themselves.
Throughout the research period with Libihini working with a quantum computer, one of the questions that we always asked ourselves is, how do you visualize the work that is created with a quantum computer? And what is the aesthetic that can be developed? The idea here was not to create this educational or encyclopedic experience of a quantum computer. It is not about setting out a set of definitions, but it's about offering audiences an insight into the world of quantum computer through an experience and through the experience of art. This exhibition by Libihini and this new LAS commission is taking place at the Sharing Foundation here in Berlin. The Sharing Foundation is an organization that works across the arts and sciences. We felt completely aligned with the mission of the foundation.
Quantum computers aren't yet fully developed, but when they are, undoubtedly they will change the world. They can model materials more precise than any digital computers, because obviously materials are based on quantum particles like atoms. This could lead to new drug design, better energy storage. Quantum computers can also model like complex phenomena very well, like the climate and things that are really critical for like where we are in the world today. On the other hand, quantum computers are being deployed and developed by big tech companies that have actually got dubious track records with how they've used artificial intelligence in the past. And if they're used in this way, it could really sort of escalate this idea of sort of surveillance and like kind of change what's possible in terms of privacy and access to information. So I feel it's really important to use art and other means to really start asking questions around what quantum computing means for society before these systems become embedded within our wider digital infrastructure and therefore very difficult to change.
So Ent, you can see playing in the background of this video. This is the installation view from London, from Arbeit Gallery. So you can see what I've been doing in part is visualizing and tracing some of the invisible processes from within quantum computers themselves. So I've been working mostly with data from different quantum entangled states, because the patterns that you get in these data, in this data are kind of unusual or strange compared to patterns that you would get from, well, you can't even create entanglement within digital computers. So these are kind of, at the moment I've been working mostly with quite small quantum computers, between 5 and probably 25 qubits. But this gives you quite a rich visual language. And I've been using this data to animate images and 3D models, and these have been built into this world using a games engine, Unreal Games Engine, working with a team of developers to kind of create this world that's very visceral, enabling audiences to really feel and perceive and use their bodies to understand quantum computing. Now, there's an art critic called James Elkins that wrote a book called 6 Stories from the End of Representation. And in the final chapter, he really talks about how quantum mechanics, and therefore we can extend that to quantum computing, is beyond visual representation. So what that means is I'm capturing traces of these invisible processes, but because quantum states or the systems within quantum computing exist in much higher dimensions compared to the Newtonian, the macroscopic world, it's impossible to kind of visualize everything at once. But we could start to glean traces of these, and this is what I'm using to animate many aspects of Ent. So these creatures, ebb, flow, the colors, the landscapes, these shifting movements where objects deconstruct, become boundaryless, formless, and then come back together. This gives audience members a sense of what's going on inside quantum computing visually, as opposed to kind of either having to understand the mathematics or hearing a lecture which might be kind of more challenging to understand if you're not well versed in the concepts of quantum computing. So the work Ent draws on a very famous painting, Hieronymus Bosch's The Garden of Earthly Delights, and it's a quantum reinterpretation of the central panel. Now, depending on who you read writing about Bosch, there's different interpretations of the central panel. Maybe it's a celebration of desire and lust and carnal pleasures, or maybe it's a condemnation of those. Because Bosch, of course, was very Christian and lived within a Christian society. I love that ambiguity because it relates to me a lot about the uncertainties within quantum computing, not only the uncertainty at the heart of quantum physics, but also the uncertainty around which way the future of quantum computing will go. The central panel of Bosch's triptych is situated between heaven and hell. So in some sense, my work is asking which way, will these new tools lead us to kind of a more utopic situation where many people benefit, or a more dystopic situation where only the people who own these really powerful new tools benefit from the technologies. You can see in Ent behind me now that I've really centered hybridity, the hybrid. So audience members encounter these hybrid creatures, and then these are then animated using quantum data. So it's really a celebration of the hybrid. And for me, the idea of hybridity really connects well to quantum superposition, where one or more particles or or systems can be in multiple states simultaneously. So if I were in a superposition, could be here and in Berlin at the same time. Obviously, I'm just in London right now. And also in entanglements where two or more entities almost lose their own identity and merge together in a symbiosis where even if you try to even get an individual out of an entangled system, you end up destroying it. So these concepts right at the heart of quantum really lend us to new ways of thinking about individual entities where we're no longer just by ourselves, but we're really connected to each other and other beings, other people, other aspects of our world. Obviously, I'm using these metaphorically, but it does lead us to a new way of thinking. Of course, historically, the notion of hybridity was related to contamination. In Bosch's time, hybridity or hybrids, these monsters in his drawings were creatures that were out of place of God's natural order of things. So they were unpure and therefore sinful and symbolic of kind of the animalistic sides of human nature. Whereas I'm trying to really celebrate these things in my work as opposed to kind of some centering hybridity. And so I think quantum computing could lead us to new ways of understanding life and our place within the world. You'll notice in my work there's actually no human bodies. In Bosch's triptych, the central panel is full of naked humans experiencing carnal desires and pleasures. But actually there are humans in my work and they end up being my audience members. And while they may not be naked and, encountering each other through touch, what a lot of people do in these immersive installations is start filming the work. So they start filming the artwork for Instagram. And immersive experiences are very Instagrammable. So I'm sort of showing how our desires have changed over time. Now our desires are for new technological experiences, for new artistic experiences. And I'm questioning that. What I'm trying to say is like how much should we desire the new? Or is that fraught with dangers in some part? And I hope people reflect on this. At some point in my work, in End, the worlds collapse. So rather than these luscious forms that are breathing, animated by quantum data, the worlds desaturate, so they lose their colour. And the forms collapse to the ground under gravity. So they become ruinous. They become less enticing. And this happens at random points in time. So in some sense, the work has its own agency and it pushes back on this Instagrammable experience. It doesn't give itself freely. And this also references quantum collapse. And then at Republica Festival with the Goethe Institute, I'm showing some additional video works that were commissioned by a gallery in London, Arbeit Gallery, where End is now being shown. And these new video works really allow me to talk more about the themes in End. But what I've done is created a fictional quantum computing company called QX. All quantum companies need a Q in their title, you'll notice, except for a couple. So these videos are really fictional videos that are like promotional or product launch videos for this company QX, which stands for Quantum Experience. And what this allows me to do, again, I'm using art as a vehicle to discuss wider themes around quantum computing. And it allows me to reflect on how art made by quantum computing can be appropriated, or you might say kind of used for the capitalist endeavors of big tech. Also, in the vertical videos, you can see some examples next to me right now. It really introduces audiences to narratives around quantum computing. Here, I've been lifting text directly from big tech companies' websites. So companies that are developing quantum computing and startups So it allows me to, I'm really thinking about what are the words, what are the narratives around quantum computing right now. So in a gallery setting, these are quite strong advertisements for quantum computing, and also allows me to introduce audiences to potential applications around quantum computing. When they're fully developed, what will they be doing? The dominant narratives around quantum computers are generally economic, how much money they'll make us, or I say us, I mean society, but it's generally the people who own the tools or own shares within the tech company, of the tech companies themselves. And also there's lots of geopolitical narratives to do with security. When quantum computers are fully developed, maybe in like 5-10 years, once error correction is sorted, which is a difficult problem, quantum computers will be able to decrypt current RSA encryption, the current blockchains, and there are solutions for this, but this is something that governments and tech companies are really working on at the moment. There's almost like an arms race between the West and China. The tech tends to be owned as well by the global North, further sort of generating further inequalities between the global North and the global South. So previously, in a lot of my artworks, I've made a lot of work around artificial intelligence. I'm currently an awardee for the Mozilla Foundation Creative Media Awards. So I've been exploring biases in AI, how artificial intelligence and machine learning systems might prejudice against the working classes, gender, different types of bodies. So thinking about, able bodies versus disabled bodies, and how this really comes from historical and cultural biases in society, and how these biases gets translated into code. So in my work that I'm showing here with the Goethe Institute, and that was commissioned by Arbeit, is really thinking about how quantum computing can tap into this kind of surveillance capitalist use of new technology. So Zuboff, I'm sure many of you have read her book, The Age of Surveillance Capitalism. She really talks about how digital technologies like machine learning are used by big tech companies. They use social media platforms and the internet to gather lots of data about us and our preferences, our data about us. We often don't know what's been taken, and it's sold to advertising companies and other companies, and that can be used to sell things to us. I've noticed recently that adverts for myself are getting more and more accurate. And I'm sure you've heard about how Facebook has been used to sway elections and so on. And I'm really, Zuboff writes about how this sort of digital manipulation really acts quite often under our awareness. So it undermines our agency and our free will. Unless we start having these conversations about what's going on, and then we're really able to become aware and to some extent fight back, although that's quite difficult for the individuals. So one of the big areas of research in quantum computing at the moment is quantum machine learning. I think it's last year, 2021, IBM Summer School was on quantum machine learning. I'm sure I'm pretty certain Jens, who's moderating this panel, has many papers on quantum machine learning. I'd be surprised if he doesn't. And and because of how machine learning has been used by big tech companies, as documented by Zuboff, I'd be very surprised if quantum machine learning is not used in the same way to exponentially extend modes of surveillance capitalism. And no one's talking about this. And this is why it's so good, for me at least, that the Goethe Institute has set up their program, Living in a Quantum State, to deal with some of these ethical questions. So I explore this in relation to art in one of my videos that's being shown here at Republica Festival, how big tech art washes, and how they might use entertainment as a distraction mechanism. You know, Instagram is very entertaining. As an artist, I'm often on it. I mean, it's almost necessary to promote what I do, to make connections, and I'm distracted by it. Yet I know I'm feeding into this surveillance capitalist mechanism. And that's why I feel that when people were filming my artwork end, they're also really sort of feeding into this new all-seeing eye, this godlike technology apparatus that really knows what we're doing and what our preferences are all the time. So new types of, and also my video deals with new types of analytics from quantum computing. So I suggest you go and watch it. But my last comment before I go is, all is not what it seems in my video. Throughout the 3 videos, there's quantum glitches that overlay the work, that suggest perhaps there could be an alternative way of using quantum computing, but values the plural and entangled rather than this linear accelerationism, solving problems really quick that couldn't be solved on digital computers. Perhaps artists and others could use quantum computing to really reveal this plural weirdness at its heart, and kind of understand how we can work with this weirdness to understand new forms of connectedness. I've been using slime as a motif throughout my work. I think slime is an excellent metaphor for quantum physical particles. Quantum particles aren't rigid, they're fluid, and they extend like waves across space, and they can become entangled like if we merge 2 slime balls together. Now, obviously, I'm using this as a metaphor, but it really enables people to go and touch the slime and feel it with their own hands and understand by doing. I encourage you to go and play with some slime at the exhibit, which I believe the Goethe Institute have some slime for everyone to touch, which is excellent. I'm also investigating the slimy world of big tech, how big tech companies can appear friendly and benign, particularly through the messaging that they send out, but actually may be quite unpleasant with their tentacles that plug into our lives like puppet strings, manipulating different aspects of what we do. Slime obviously is related to contamination and disgust. Yet it can also be playful and interface, linking inside and outside bodies in a liminal space. So it holds these multiplicities of meanings that I think are really useful to help describe quantum computing and how it's situated in our society in a way that's so accessible and playful, which I think is really a good way to, like, I'm not just trying to big myself up, but you know, these technologies can be difficult. So I think we need to find new ways and new languages to describe them to people. Like Ent, like the themes in Ent, the slime in my work represents a double edge of quantum computing. Like any new technology, how it's used depends on the social, political, economical systems that it's embedded in. So scientists tend to be quite positivistic, really celebratory around the new, don't really think about anything being in a critical sense, or perhaps they don't really understand the ethics around these technologies. Not always, but I'm talking in generalities from my own experience. On the other hand, technologists tend to be, and the technology firms are chasing profit, because we live in a capitalist society, of course. So I'm inviting other people, artists, people working in the humanities, journalists, to enter the critical debate around quantum technologies now, so that they aren't fully developed before we have these new languages and understand what they'll be able to achieve and how they'll impact us in the future. Thank you.
Wonderful. Actually, that was literally the first time I saw this video myself. That was quite insightful. Okay, wonderful. So we have 10 minutes left, which means that we have 10 minutes for the most important part of this session, which is you. So now's your chance. Feel free to ask any questions to either Jasmine or myself on quantum computing, the capabilities, the potentials, the risks, where we are, where we stand, about everything. Here we have a mic here. Just feel free to ask questions. I will ask questions. So your only way of defense is coming up front and asking your own questions, because otherwise I will bore you with loads of questions that you might not want to hear. So come to the front. Oh, that's already the first. Wonderful. That's good. Yeah.
Hi. I hope you can hear me. My name is Fiete. I wanted to ask if ever you can use entangled quantums for communication. So to break the law that that information cannot be faster than light. If you have one day, can you have entangled quantums and transfer information from one point to another in no time? Will it be possible?
Wonderful question. Do we take rounds? Yeah. Who answers first?
We can, but this is a fast answer. No, it won't be possible to communicate with this faster than light. You can use entangled particles to communicate securely, but not faster than light.
Yeah. My answer is indeed, that's right. I mean, quantum particles can be like more strongly connected than classical particles. That's right. So measurements on one side seem to have an effect on the other side. That said, this only manifests itself in correlations between you there and me here, but you will not be able to send information. As Jasmine says, you can use this in clever ways to do exciting things, but you cannot literally have a causal influence. That would be, then you could talk to your dead grandmother and you would violate causality, which might be interesting, but that's not possible according to the laws of nature.
Yeah. That was very interesting, Jasmine. And I just wanted to ask, maybe both of you, if what you see in a quantum computer is effectively all of the refrigeration, I was just wondering, what is the actual energy requirements of a quantum processor?
Who answers?
Yeah, it depends a bit on the platform you use, I guess, but many platforms need cooling, for example, and this uses a lot of energy. Yes, okay. It depends what platform, but
yeah.
The quantum particles itself, they don't need more energy to propagate or to survive, but just more the surrounding. That to detect particles, you often need superconductors, which needs to be cooled at very low temperatures, and this costs energy. But for example, if you use photons instead of light instead of electrons, then you have less heat which is generated, which people also use. So it also has some advantages in terms of energy.
Okay. Shouldn't that be part of the questions and the discussion around quantum computing, its energy impact, rather than introducing a completely new type of computing, which could actually be much more energy intensive?
Yeah.
Yeah, with quantum computers, you would invest more in. With quantum computers, you can't solve problems which you will never be able to solve with classical computers. So this is why I guess people would be willing to put more energy in this, even if it's more energy. But also, since quantum computers, I guess, will not be, not everybody will have a quantum computer at home. It will be more like specified quantum computing centers, if this will come maybe. And then you have at one point maybe more energy consumption to solve very hard problems, but in total this is then still a small amount of energy. And the normal computers you use, everybody then will be the classical normal computers still.
Yeah, maybe we might, my 5 pence worth. I mean, the devices shown here were mostly like superconducting devices, and what you saw was like a so-called dilution fridge, a helium dilution fridge with lots of rounds. There's a fridge in the fridge, in the fridge, in the fridge, and the little pieces in the middle is the quantum computer. That said, I mean, there's lots of concerns that have been addressed. I mean, the energy consumption is probably the least of all worries. And actually, interestingly, while it's true that most of the energy goes into the cooling, in principle, quantum computers could even be made reversible and like use very little energy in contrast to classical computers, who through like erasing information must need power and energy to reset the classical computer. So it's kind of interesting that there's a fundamental limitation to classical computers that relates to energy consumption.
I have one question on how exactly a computation works on a quantum computer, because in classical computing, of course, we really want to know exactly what each bit is doing, and it has to be precise. And I find it so confusing to understand that in quantum physics, it's you want the superposition, but how can you control it that you really get out what you want? I feel. Or do you do like computations where you already know the results, then you do it on a quantum computer, and if you get the result you expect it, then you know it worked? But how do you approach
Shall I start and then you take over? Or?
Yeah, maybe, because this is actually a very good question, because I forgot to mention this part in my talk. Because I explained this interference, and that if you can destructively interfere if you have a positive and a negative superposition, for example, kind of. And this you can use then you have the superposition, so you have kind of all, if you want to say it in this way, you have all answers all at once, but with this interference, you can make it such that the wrong answers interfere destructively, that they are kind of gone, like staying in the pub, this is gone, and that the right answers, this what you want to have, gets enhanced.
Maybe to add my 5 pence worth to link this answer also back to your question, which is, I mean, the programming of a quantum computer is actually quite similar. In fact, like when you talk to people like in Innsbruck, they have like these sophisticated experiments in the cellar, but they sit in the third floor and they're in their lab, program things, and it's really sending classical signals, classical programs to the machines, and the machines are doing something, and yes, they are manipulating the quantum state in the way Jasmine has explained with superposition and entanglement, but the control is purely classical. It's really like a program, and the software is also purely classical. Yeah.
Hello. Yeah. So, at the very, very beginning, you mentioned how algorithms can be solved using quantum computing, and you've also mentioned big corporations and perhaps in small brackets or big brackets, evil people getting hold of quantum computing. So how does the future of secure banking transactions look, and how would you maintain the security when people have access to quantum computers on a wider scale? Oh, and there's a very famous BBC sitcom about the army, and does this mean that we're all doomed?
No. I mean, okay, there's two things that come into play here. One is, yes, like with great powers comes great responsibility, as we know from the Greeks, right? So surely we have to be aware of these matters. Now, it's true that, as Jasmine has explained, quantum computers can break like modern crypto systems as we have them, like RSA-type settings. Although there's also post-quantum ways of doing that, we shouldn't be too worried about this. At the same time, quantum mechanics also provides also the fix to that through quantum key distribution. So there's even quantum ways to protect your privacy or privacy against that. So there's even ultimately secure ways of communicating and not allowing eavesdroppers to come in, even if they come from the evil side, whoever that may be. But you can protect your communication from other people. So, yeah.
So with quantum communication, you're really on the safe side, I would say, compared to the encryption we use today, because you cannot. It could also be that there's a classical algorithm which breaks already our encryption. It could be nobody can dispute this, but with quantum communication, you're really on the safe side.
Yeah, there's also even quantum-inspired classical algorithms. So let's have a last question. I think I get notifications that we are running out of time, so it's your privilege to ask the last question. There are more, but yeah.
Okay, I keep it short. So thank you for the presentation as well. It was really insightful for someone who's not from a physics background as well. So my question is more to ask, could you speak a little bit more to the interests of, for example, military or technological companies, like big tech companies, in what sense are they looking for solutions for their own problems, or what are they most interested in the way that they expect quantum computing to be helpful with? And maybe a second question, if I can squeeze it in, just a short one. In what sense do you see the influence of those public or private interests happening also, or affecting research agenda at universities, for example, speaking of public-private partnerships. In what sense do you see that happening at a university level and interfering maybe in a way? Yeah, sorry.
Do you want to start? Shall I start?
Yeah.
Yeah.
You can start.
Okay, then let's be quick. First, military. Yeah, I think, to my assessment, like the most attractive, well, in cynical terms, a feature of quantum mechanics for military entities is presumably quantum key distribution, quantum communication, maybe via satellites, where you can really communicate to all places on Earth in principle, in principle, unconditionally secure fashion that surely has a military implication in principle, so one should be alert of that. Tech-wise, of course, big companies are like doing things. I mean, like Google, IBM, Rigetti, and the usual suspects are heavily investing there, but also other entities like chemical factories and so on are coming into play. One number I know out of my head is that today about a billion CPU hours are used every day to compute properties of quantum materials. And quantum material research, or simulating complex quantum systems on quantum devices, is surely an application that's interesting for pharmaceutical companies, for chemical companies, and so on, that has surely in principle also the capability of producing like insights, wealth, and major revenues, but that's truly one of the big applications. Last, how is that changing the ecosystem? Oh, don't get me going. I mean, we have a couple of seconds left. Surely it does change things. It's interesting. I mean, I'm a dinosaur of the field. I started 20 years ago with a PhD in the field. Quantum computing was a dream for many years. Only within the last 2 years, these machines are being built mostly by companies. And that creates an interesting state of affairs, mostly for the better. But it also creates an interesting, refreshing tension, I would say, between academia and industry, which messes up things mostly in interesting ways, I would say. But there's more to say about this. Jasmine.
Yeah, I guess we're done with the time. But you also mentioned the funding. And I think at universities, we are also funded by the general public mostly. So one doesn't need to worry too much.
That's right. And quite generously, I should say. Okay, good. There's more questions, but thanks for the interest. Thanks for the many questions. Thanks for the wonderful presentation to both of you. And thanks for listening.
Okay.